the GPU execution model. So it is central to the GPU execution model is a concept of kernels. The kernel is performed by execution of the kernel is performed by launching in parallel a set of instances, so many times the kernels. The number of instances and their organization is defined by the following element. Work items, this is equivalent to a thread. Work group, this is a set of thread. And ND range. ND range is set of work group. Let's look at that in more details. So this is a kernel. This is OpenCL syntax. We will see more of that later. So this is a keyword kernels. This is a keyword to say this is the data in device memory. And when you start, you have in here an ID. Okay, so that's the instance ID. And when you execute this kernel, you create multiple instances, that is work items in here, or CUDA subs or threads, and you launch one with different IDs, depending on the name or the size of the ND range and of the work groups. In here, what is important to note that in the execution, the threads, the work items, are groups in subset. And this is what is called CUDA warps. We'll see the implication of that later. So the work items is the unit of concurrent execution in the GPU. This is another name for thread. It's the execution of a kernel instance, a single kernel instance. And work items are executed in lockstep way. So single instruction, multiple data. So in a subgroup of work items, they all execute the same instruction at the same time, but on different data. So work groups. So the work groups is a 1, 2, or 3D, 3-dimension set of work items. Okay. Each work in the work group, each work items have some coordinate, and you have a set of work groups defined by the ND range. And each work group itself have also its coordinate in the ND range. If you take CUDA, this is a grid in CUDA. The work group are thread blocks in CUDA, and the work item are CUDA threads. The synchronization to the execution model, you can have barrier, but only inside a work group. You cannot have a global barrier like that. Okay, there is no mechanism inside the GPU to synchronize all the threads, and one of the reasons this has been done this way, it's because it's a huge chip, and it would be very, very costly to implement such a barrier. If you want to have a global synchronization, you have to create 2 kernels, and then you will get the synchronization between the execution of the 2 kernels, and that will provide you a global way. This is not very convenient for programming, but this is the way to get it. The execution in lockstep. So, if you take a subset of work items, that is CUDA, this is in CUDA, this is warps. Okay. The execution engine of the GPU will execute always the same instruction. So I will first execute I1, then C2, that's a conditional, then I3, etc. And the problem with this model is when you get to an if. This is an if. You have the true branch and the false branch. So if you want to execute the same instructions, what you have to do is to mask the instructions that are on the wrong branch so they don't have effects. So the thread for which the if is true will be executed. The one for which the if is false will be masked to avoid changing the state of the machine. So the execution will look like that. So I have C1, everybody is executing I1, everybody is executing C2, the conditional, and for some thread the conditional equal true, and for some other thread the conditional equal false. Okay, so in one case I need to execute the true branch, in the other case I need to execute the false branch. But all the thread will go through all the instructions. So after the if, the thread for which the conditional is true will execute the instructions, they will have an effect, and the thread for which the conditional is false are masked, the instructions are masked and won't have an effect on the machine. So that will go like that, and then I reach the else, okay, and I swap the mask between the thread. So now the instruction with the condition equal true won't have an effect when I am in the false branch, etc. And then I unmask everything and continue the execution. One of the nice things with the work item and thread executions, when I have a warp, so all warps will be doing a memory, all thread work items in a warp will be executing a memory accesses. So if I want to pipeline, I need to take another warp, another subgroup of the work items, and I can pipeline them. In this way, I will keep my machine busy. If I have enough resources, I can even pipeline between work groups. So this way I will have many threads in flight. So the one in parallel inside the warp and the one pipeline and the pipeline between the warps. So the questions for today: what property of conditional instruction is detrimental to performance? How to implement global synchronizations? What is the impact of the ND range and workgroup size on the resource uses? Why is GPU performance very sensitive to problem size? For this question, wait to see the memory model. You need the information there. And there, you must note that if all work item in a warp have the same condition, have the same mask, then only one branch of conditional is executed. Okay, we'll discuss that in course anyway. Some reference, you can look at this tutorial on CUDA. It has a lot of explanation on GPUs, and it's on Piazza. So I put it in the resource part. Okay, see you in class.